This is part 5 in a series of videos in which I'm attempting to repair a Wren executive computer. In fact, I've got 3 of them to repair, but I'm also attempting to start a collaborative project to get people involved in reverse engineering both the firmware and the hardware for these machines. I think there are quite a few of these around, and they do seem to have been fairly unreliable, so I think a lot of them are possibly sitting around not used simply because the owners can't boot them up. A secondary issue is the availability of boot floppy disks, which has been a major issue trying to effect these repairs and the reverse engineering simply because none are available. So I've been working with a few people trying to put together some working floppy disks, going from images that we've managed to obtain, old floppy disks. I've been trying to recover data from some of the old disks and had a degree of success, but where we are at the moment is I'm trying to fully resolve the mapping for most of the devices on this main board, and if I can do that, then I can make the firmware files available to anyone that wants to get involved in the project, and then we can start looking at doing a proper documented reverse engineering of the firmware, and that will really simplify things. As part of this process, what I wanted to do was just go over a few more steps that I'm taking and how I'm going about figuring out firstly where the faults are on this machine, but also how to resolve the memory map for this machine. If you watch the previous videos, then you'll know that I'm putting together a chart showing where all the devices and all the registers are mapped within the memory space of the Wren. Now it's a Z80 processor, and a lot of the devices are accessed through the in-out port system of the Z80. And one of the first things I've been looking at is the information that's provided in the Wren user manual, and this is really the only technical documentation I've been able to find at all, and it just gives a range of tests for the built-in self-test. But it is quite useful because the way they've worded it, we have things like this where it says ROM bank 8, ROM bank 4, and when we look at the source code in the 2 ROMs, we can see that there is bank switching at the beginning of each ROM, and it appears as though they are being referred to by banks 4 and 8. So reading through the rest of this, it would seem that we have some SRAM at bank 0, and this all tends to indicate that there is a bank switching system, so we have some sort of bank switching system going on within the Wren, and then looking at how this is being implemented in the source code. If I just grab the first part of the source code, so if we look at the first part of one of the ROMs, the beginning of each of the 2 ROMs is identical except for the address that it's trying to switch to, or the bank, but it seems to be writing this value to port 0, and that would tend to indicate that port 0 on the board is where the memory bank switching is mapped to. So we can test that. That's the first thing I want to do. And in order to go about this, the way I've got the system set up at the moment is I've removed the logic analyzer, and I've got the Fluke 9010A Z80 AA pod attached to the Wren board. I'll just move the camera so you can see what's on the other side, and I've got the Fluke sitting over there in the corner. And so what I intend to do is see if we can manually switch to the different banks within the system. So what I'll do to start with is try switching to the 2 ROM banks, that's bank 4 and bank 8, and see if we can actually read data values there. So I'll just move the camera so we can see the Fluke. Okay, hopefully you can see that. Unfortunately I can't get everything into shot at the same time, but we should be able to manage by looking at just the screen on the Fluke. Now if we look at the source code, so if we take an arbitrary address in the source code for the two ROMs, this is one of them. If we take address 100 for example, then we'll see here that at address 100 there should be a value of 2e, and if we look at the same address in the other ROM, we can see that the value at that address is 3e. So the two values we need to try and read using the Fluke is 2e and 3e. So what we'll do is we'll power up the Wren. I'll just boot it up. It's not going to start up of course because we've got the Fluke plugged in place of the Wren's processor. But I'll power it up, and now what we'll do is I'll select run UUT. This will just get the Wren to go through some initialization if it's capable of doing that. Okay, so there's nothing showing on the Wren screen because the Wren isn't going to be running properly at this point. But what I want to do is stop the processor from running, and I'm going to write a value to the what I think is the bank switching port, which is at port 0. So if we select a write to port 0, which in using Z80 on the Fluke, we select this address. So 4 digits is the memory map space, and then everything above that is the in-out port space. So what I've done here is select port 0, and I want to write a value of 8. So that will give us, in theory, if we're correct with the mapping and the way the ports and memory bank switching is arranged, that should select the bank for one of the ROMs. So we'll read address 100, and we're getting 3e, which is correct for one of the two ROMs. So if we look at this particular listing, we can see this is 3e. We'll just confirm this by selecting the next address at 101, and it should be FF. So if we read 101, it is indeed FF, so we can be fairly confident we're looking at this ROM. If we're right about the bank switching, we should be able to switch to the other ROM by writing a value out of the port of 4. So if we write, again we'll select a port this time, so that's again the same port 0, and we'll write a value of 4, and we should now have selected this ROM memory space. So if you read address 100, we are indeed getting 2e, which is the address that we expected to get. So we've got 2e. Again, we'll check the next one at 101, and this time it should be 02. And it is indeed 02. Apologies if you see any flickering on the screen, that's just the refresh rate of the camera. Hopefully you can read what's on the Fluke display. So you can see that we are able now to switch between the banks manually on the Wren board. And the thing to bear in mind with any system like this, however complex it looks, it's really nothing more than a collection of memory mapped devices, port mapped devices, whether it be a UART, a floppy drive controller, a display controller, SRAM, DRAM, it really doesn't matter. From the perspective of the system processor, and that's how you have to look at these, is you should in theory be able to access any of the devices and use them successfully in the way that they're meant to be used. So if we take the next logical step and go back to our memory map, what we have here is SRAM mapped again to 0000, but of course it must be in a different bank. We can't have all these, although they're all mapped to the same physical memory space, they're in different banks. So if we switch to what we believe is bank 0, which is what it's saying here should be for the SRAM, then we should in theory be able to read and write addresses. Now if we try and write to 100, so if I read 100 back here, then it's 2e. So I'll try to write to address 100, and we'll try to write a value of 55. It's saying it's written to that address, but if we try and read that back, it's still saying 2e, because of course this is a ROM that we're looking at the moment, it's not a RAM, so we can't modify the contents. However, if we switch to bank 0, so that's the correct port number, and this time instead of 4 or 8, which are the two ROMs, we'll set 0. Then we should in theory have switched to the SRAM bank, and if we try now to write a value, again I'll try to write to address 0. In fact, what I'll do is I'll try to write to address 100. So 100, and we'll write a value of 55. And this time when we read back 100, we should see a value of 55, and we should be able to modify this if I try now to write a different value to that address. And we'll read it back. As you can see, we are looking at RAM on the system board. So in other words, what we can do when we have a setup like this is figure out using the logic analyzer what each device address mapping is. If it's in a different bank, then all we need to do is figure out how to determine what bank it's in, which we'll look at in a minute. And then once we have that information and this table's fully populated, then what we can do is use something like the Fluke to write data to the various areas. And more importantly, once we've got the bank selected, so now we've got the SRAM bank selected, what we can do is run something like a RAM test. So if we want to run the RAM test from address 0 up to, we'll go up to 100, go to 110 since I've typed it in. Then it's now going through. You can see we've got an error here. So there's obviously something not right with the SRAM, and this is the power and the beauty of a machine like this and this setup, is that we can start going through looking at the various devices, selecting the correct bank that they're in, and then doing some fairly in-depth testing from the perspective of the system processor. So if we do have a weak IC, for example, it's not got quite the right signal level, then it's going to be intermittent, so we'll try repeating this test. And you can see this time it's passed. So this tends to indicate that we have an intermittent issue, most likely with a buffer between the system bus and the memory, the SRAM. It's unlikely the SRAM itself is faulty, it could be, but at least now we have something to start looking at, and we can start putting a scope on those lines and see if we are indeed getting poor signals. That's most likely what's causing this Wren not to boot up. Is the ICs will almost certainly test okay if you take them out and put them into an IC tester, but when we try to run them in the system, then because the Wren's running at quite a high speed, around the 12 megahertz, and TTL, especially the TTL of this era, was really struggling at that speed, and the board layout's not that good, so that combination means that it's very prone to just tripping over itself and stopping working. Now let's move the camera back to the board and we'll look at how to determine what bank a device is in. Okay, so looking back at the board, what we're actually looking at here is I've got the scope connected to the chip select line of one of the two SRAMs, and I've got the Fluke to continually cycle through the memory test that is accessing this particular SRAM. And we can tell that we're on the right bank because the device is actually being selected, and if we switch banks then that will stop. So this is a very good technique to figure out the bank a particular device is on, and also we can use the logic analyzer to figure out what particular address any particular device resides at. And it's not, you're not restricted here to single or individual ICs. So for example, the DRAM bank is 8 ICs plus the buffers, etc., and the refresh, everything else. But using this method you can write and run test scripts to fully test the memory. If it fails or if it's intermittent, you can track down what's going on with a scope. All you do is write a simple short script just to write values to or read values from the memory or whatever device it is you're trying to test, and then you can scope all the individual address lines and data lines and see where the problem lies. It's almost impossible to do that when you're running the system firmware, because the system will just be running through all manner of different tests. In fact, I normally write specific ROMs with slight modifications, as I've done here, just to make sure that I've got a bit more control over the system. I can halt it and do various things. So what I'm going to do now is work my way through the rest of the devices. I'll try and figure out why this SRAM is failing the test that we're trying to run on it, and I'll go through testing all the other devices. Things like the floppy drive controller you can even run manually if you want to. You can send a command to get it to drive to a certain sector or a certain track, and you can do this with all the devices. Some are dynamic and you can't do it that easily, and others are very straightforward, like DRAM and SRAM, just write values into them and read them back. Sometimes it's useful to keep it running for a while and see if it is reliable. Sometimes it'll work for a while then stop working. So as I say, what I'll do is I'll go through the board, I'll test all the major devices. If I find any faults, then I'll replace the relevant ICs. I've been finding a lot of faults with the buffer ICs and latches on this board, so I've been replacing those as I find faults with them, and I suspect that's what I'm going to be finding on the remainder of this board. So I'll go through the rest of it and then we'll come back if I can make any progress. Okay, so I've been working my way through the board, testing the various parts, and using the Fluke it is quite straightforward. I can run some very specific tests on this. It was actually the SRAMs that had failed. Only one had failed, but I have swapped them both out. I'll put sockets in just to make it easier for future support. Calibrated the floppy drive controller chip again. I had already calibrated that, so that seemed to be fairly close. I found a few other faults, a couple of broken tracks, and it's just minor things like that, but using the Fluke it was very easy to track those down. It's just if you're trying to write a data value to something or read it back and it's either inconsistent or doesn't work, then obviously there's an issue there that needs to be looked into. I tend to mark devices that are suspect, and I've got a couple here that are marked, so I don't know if we still have an issue with these. They're working, but the TTL output levels are low, so this may still cause an issue for us. This is part of the glue logic for the display. Display seems to work, but we're getting artifacts on the screen now and again. I suspect it's these chips that are causing that. The rest of it seems to be working fine. So what we'll do now is I'll reset it all, boot it back up, and then start doing some more testing and see if it gets any further through the boot process. What I'm really looking for is for the head on the drive to go from the first track. It should move on to another track, and then it should jump to the boot part of the bootstrap loader on the floppy disk. And I think what it's doing, this is what I want to look at really, if we can, with the reverse engineering of the firmware, is start with this element of the system. And I think it's loading a bootstrap loader into the SRAMs and then handing control to that, and then that's going through and reading the contents of the floppy disk into the main common RAM. And that's why it wasn't getting too far, because at least that's what I believe it was, because one of the SRAMs had failed. So it's loading data into there, but then when it tried to hand control to it, it just fell over and the system just hung. Okay, so we'll try booting this up and see what happens. There is no floppy disk in the drive, so I just want to see if this will come back to life. I've obviously been making quite a few changes to it, and we've got the logo on the screen. No real artifacts that I can see at the moment. They did tend to come and go, and it was worse when it was hot, but like I said, I think I've got a couple of ICs I might need to change. Try a boot disk and see if it reads. It was reading the first sector before, if you recall, but it wasn't really going through the boot process reliably. Okay, that's looking quite promising. I'm not quite sure what the boot process is. Okay, right. What I'll do is I'll move the camera across so you can see the screen a bit better. I think I need to turn the brightness down, and we'll see if the machine is working at all. Okay, hopefully you can see the screen fairly clearly. What I'm going to do now is I'm actually going to switch the Wren off and try and reboot it. So I want to make sure that we can reboot. I don't want to have this as we go through some testing just to find out we can't repeat the boot up. So I'm going to pop the floppy disk out of the drive, turn the Wren off, and give it a few seconds, switch it back on. Okay, and I'll put the disk back in and see if it boots again. It's always best to do this. It's if you're getting unreliable booting, then you still have issues that need to be looked at before you go any further. But yeah, okay, good. It's booted successfully a second time. Now I've never used a Wren, so I don't really know what I'm doing here. So we'll have to just guess. So along the bottom we've got set to time, directory A, directory B, and F1 to take us to CPM. And we've got various utilities. Presumably we can navigate through these, can we? No, we've got copy disk system, but I don't know left and right direction. And of course I'm pressing the keys on this keyboard here, nothing's happening, and that's not really that surprising because the keyboard that's plugged into the system is the one that's over there. So this is the sort of thing you do when you get overexcited. So I'll try pressing the keys that are on the keyboard that's actually plugged into the board. And yeah, okay, that's now moving. So okay, that's looking good. As I was pressing the keys on the wrong keyboard, this is not plugged into anything. So what I'm going to do is just try pressing a few keys. I won't go too far into this right now. Well, one of the first things I want to do is to try and make some copies of the system disk. The system disk I've just booted from is one of the original boot disks that we managed to get hold of. It's in a very poor state, and I've managed to recover most of the data on it, but I don't know how long that's going to last. We do have another one that a friend made up, and I will try that and see if that boots. But really what I need to do is get the machine to make its own copy, and that way we can be fairly confident we're going to get a good copy of a bootable disk. Okay, so next thing to try is I'll try pressing F2. It says that should give me the directory listing for drive A. Indeed it has. Available data space, 2K left, and so okay, we're looking like we have the system up and running. So pressing a key to continue takes us back in, and what I'll do here is try pressing F5 and see if we get into CPM, and we have. So it's booting up. We've got the prompt. So it would appear that we have a working system. What I'll do now, on this on camera, I'll go through and do some proper in-depth testing of the system. Because we've got CPM running, I can write some fairly good test procedures from within CPM and fully test all the different parts of the system. I'll also read through the Wren manual and see how to properly run it. I've also got the utilities disk that came with the Wren, so I'll be looking at some of those. And once I've got this figured out, I'll post a video showing the Wren in operation and try and demonstrate some of the things it can do. So the good news is, of course, we've got a working Wren, and that means that it will be much easier now to reverse engineer the hardware and the firmware. So what I'll do once I've tested the Wren is I'll finish populating this, and then I can put the firmware decompiled files and this file onto my website, and then we can hopefully start doing the reverse engineering of the firmware. And I think the way we need to go about this is, if you are going to get involved and you need me to run any specific testing, if you don't have the Wren or access to a Wren, which you probably won't, then just drop me a line and I'll carry out the tests that you want me to perform, and hopefully get the data back to you as quickly as possible. But okay, so it's good news. Looks like we've got a big step forward in this video, and in the next one we'll start looking at how the Wren behaves, what it can do, and then from that point on we'll get properly into the reverse engineering process.